So welcome to this presentation. My name is Wette. I work at Ericsson in Montreal, Canada. So I'm going to talk about a project that we have realized with Concordia University. This is applying machine learning in network capacity planning for IoT. So I will describe the project goals, the problem we're trying to solve, and the machine learning that we have applied, data collection to traffic modeling and to capacity prediction, and then finish with the analytic framework implemented to implement the solution. So let's start with the project goal. In this project, we want to apply advanced machine learning in network capacity planning. First, we want to use analytics for designing traffic models for IoT networks, for IoT traffic. And we want to use machine learning to accurately predict traffic evolution in the future and the exact capacity requirement. And last, to use analytics in network resource optimization. So this is the classical process of machine learning, and that's what we're using in this project. So I will go through it during the presentation. So let's start with describing the business problem. So with some definition, just to describe what is the objective of capacity planning. Capacity planning in network, it's a methodology that we use to model the current state of the network and also the traffic behavior. And then with this model, we can project the future traffic load and sizing the network resources accordingly. More advanced capacity planning method can be used to even detect capacity issue before it happens. These are congestions, resource shortage. All this is to improve the customer experience. This type of algorithm also could help to really suggest to determine at what exact time, where in the network, and what type of resources need to be reconfigured. So let's talk about the problem. Today, we have network tools that we use for capacity planning. These tools are more static tools, means that they are not upgraded frequently. And they implement some kind of statistic model for predicting the capacity. They are not using the actual advanced machine learning algorithm. I mean, when I say today, it's like maybe 2 to 3 or 4 years back that we started this project. And this tool will base their assumption on some KPI. And this KPI, the main one which is used in capacity planning, is the one measuring the peak period of the traffic. And based on the peak period, we will dimension the network. But what really happens is that most of the time, resources are unused. And that's what I'm showing here in the graph. Okay, now the IoT. Why we're doing this for IoT? As you know, the Internet of Things, it's a big network. I mean, it's a 50, some projection are 25 billion devices. Some are even up to 100 billion devices, generating a lot of data, a lot of traffic on the network. So it's even bigger than current human communication. And we're going to use, and they are using the communication network. So it's a lot of traffic that is coming on the communication network with the Internet of Things. And this traffic has different characteristics which are not the same as the human communication. And as you see here, IoT touches almost all industry sectors. And each industry sector has their own communication requirement. Some are mission-critical systems. They are sensitive to latency. Some system are okay with a simple message with no delay constraint. So the network has to, if you use LTE or 5G or LTE network just to deliver simple message that has no latency requirement, it's some kind of too expensive. So, yes, so the IoT network is a heterogeneous network with different variety of verticals, variety of devices as well, with different capability. Some device can support multimedia, some can not, some are low power devices. And the network has to support all these different requirements. IoT is a growing network. The traffic model are not known. We know the current traffic model, but every day we keep creating new IoT services and adding this on the network. So most of the traffic models are still to be discovered. So IoT has a huge impact on the network, new traffic models that are changing more frequently. The network needs to adapt more frequently to this traffic requirement than before. Quality of service requirements are different from human communication, and this has led to the development of some category of network standard dedicated for IoT only. Okay, and the average revenue per device in IoT is still low to justify the investing in a dedicated network. So what we're trying to do in this research is to be able to carry the IoT traffic over existing communication network. So this implies developing advanced analytics to manage these different traffic requirements. And this is possible today thanks to new technology like big data and analytics, and also cloud computing, which enable to have resources, to deploy resources faster and upgrade more frequently than before. Okay, what will be the business motivation for an operator to use a solution like this? It will enable more accurate prediction of network resources requirement. When an operator invests in a network, it's for 5 or more years. They don't want it because it's expensive. So it's important to have a precise capacity planning method. And with the IoT traffic, changing models and new models are coming every time. This is challenging. We need a flexible model that it's easy to update. And then an advantage of this solution is that operator will be able to deploy IoT traffic on existing cellular network and then optimize the network resources. So what it means here is when the capacity is not used for the human traffic, this capacity could be used for IoT traffic. Most of the IoT traffic are predictable, so the operator could schedule them when they are available, when the network resources are less used. Okay, so that's some kind of a description of the context. Now let's move to the machine learning process that we are applying in this project. We start with the data set that we use. So the network, as you can see in this picture, is distributed is in the geographic area. We have radio network access, we have the core network, and we have the connection to the internet. So at each segment of the network, we have different resources that need to be planned. So we have collected radio access network, core network data, OSS and BSS data, which is sales position, configuration management, etc. and IoT data as well to understand the traffic model. And for the IoT, we have limited this to connected car data, smart city data, and smart building. And we also developed a simulator that to generate enough future traffic to test our model. So we want to apply machine learning on these different data to be able to predict the number of connected devices in the future, the transmission frequency, and the packet size. Based on this predicted value, we can now determine the capacity of the network in terms of computing, storage, and connectivity resources. And more intelligently, we can determine the capacity required at a specific time, at a specific location. And this could change over time and for a different location. So it's more dynamic than previous methods. Okay, so as you can imagine, these data come into many different formats that we cannot use we cannot input to the machine learning algorithm directly. It requires a lot of pre-processing. So these are some of the scripts that we have written to do this pre-processing. And we're also using some open source tool for that as well. Basically, we will filter the data. We're getting, just for the radio access network, we have access to like 70 gigabyte data per day. We can't use all of this. This is the way the system collects the data today for the operator that we have a collaboration with. And we have to select a portion of this data for analysis. And also, we have to clean redundant data. In IoT, devices may send there are a lot of redundant data as well. And then replacing the missing data with certain value, 0 or the mean. Removing the outliers, data transformation, because IoT, there is no data standard up to date. So data come in different standard, and to do a proper analysis, we need to transform and normalize this to transform into a common representation, and also normalize the data. And after these pre-processing steps, we enter the machine learning, the modeling step. What do we do in the modeling step? So we want to model the IoT traffic, and from this model, we can predict the future traffic load, and then the resources requirement. Doing this different at specific location, specific time. This is some experiment that we have run in Ericsson for different vertical industry, determine the size of the packet sent and the frequency of sending this message for the different industry, and also the density of the device in a specific area. We will use this information in our model. And then, before we go to we describe the model, let's see what some characteristic of the IoT traffic. Transmission, IoT device can transmit at any time of the day, which is different from human. For humans, we have high traffic during the day, and at night we sleep. But for IoT devices, some of the devices have no sleep time. Or the sleep time is not always at night, it can be at any time. And some devices are located in areas that are not accessible to humans, So the location of the devices is different from human locations. The behavior of the devices is also different. Devices that run the same software tends to behave the same. Devices could send data in a synchronized or coordinated fashion, which is not always the same for human, because devices are programmed to send information, to send data at a specific time. I will come back to the traffic model. As you can see here, the package of IoT traffic is usually short. It's not a long message as human. Device may go at sleep when it's not sending message, so it's not even sending signaling traffic on the network. And unlike human traffic, which is more downlink, IoT is more uplink traffic. So we make some investigation of some literature review to see what is proposed, and I'm going to show some of them here. This is a simple way of the basic traffic pattern for IoT. We have device that we send message in a periodic message. We have device that we send a message when an event happens. And then the last one is devices that we send large message. In reality, real-world application, IoT application will be a combination of these three basic traffic patterns. On the bottom, we have an example of a sensor. If an event happens, the sensor will go to the ED state, or the sensor could be programmed to ring at a specific time, the PU. So then we model the device using a Markov chain. This is representing when the device moves from one state to another. And we have this nice matrix here, which some kind of traduce what we have in the algorithm here. So we have modeled the traffic as a Poisson process. And the formula at the bottom is the arrival rate. So we use this model in our simulator to generate IoT traffic for our analysis. Okay. We also, just present the mathematical models. We also analyze the actual data collected from smart cities and from connected car to try to infer a model from the actual data. As you know, sometimes data is not easy to access, and for IoT, we don't have enough historic data to really predict the future. We're using simulator, and we still rely on the mathematical models and also try to adjust that with the real data. This shows traffic data, IoT data in a city in Italy. What we see in red here, it's location data analysis. In red is the area where we have more traffic. In green, we have less traffic. In yellow, we have normal traffic determined by the threshold that we have established. When we play this over time, we see that the red and green and yellow will change. So what we're doing, we're doing this exploratory data analysis to understand the traffic evolution during the day, during the week, and during the month. We also perform some correlation analysis on the different parameters. And then after the exploratory analysis, we move to the modeling and testing the model as well. But before that, my team is working on the predictive analytic for capacity planning, but we have other use cases in network management, network optimization, fraud detection, etc. So we some kind of develop an analytic framework for the different projects. And this framework contains these different models here. And as I say at the beginning, the intention here is to leverage on big data and analytic open source tools that are available today. So we're using Hadoop and Spark in data repository, data integration, and also in machine learning. We have a model for analyzing offline data. We have another model for analyzing real-time data and be able to take decisions in real time. This model is very important for us when we want to do network optimization. When we have a traffic from maybe smart city, we want to schedule this traffic. If it doesn't have a latency constraint, we can schedule this traffic according to the quality of service requirement. And if we have a traffic, let's say from connected car with high latency requirement, we can give some priority to this traffic. And this analysis is run at real time using algorithm that we have in this model. And this is one of the motivation of we're using Spark for this, because we can stream the data and do real-time analytics. Okay, we have a model for predictive analytics. This is machine learning, obviously. And also we have our simulator for generating more data for the analysis. So this shows one example of the modeling that we have done. In this case was random forest, multiple instance of decision tree. So we analyzed, we tested with different models, decision tree, random forest, and general GLM, and KNN, nearest network. And then after this test, we performed the scoring to select which model was good. In this case, for example, in the capacity planning, we end up using random forest. Okay. So in this project, we have developed model for IoT traffic, and we're using this model either in the simulator to generate IoT traffic, which helps to test different configuration of the network capacity. And we're using this algorithm, this model also to predict a future traffic load with more accuracy. We can predict traffic for each type of resources at a specific location at a specific time. And this helps to reduce over-provisioning of the network and reduce the CapEx. And the model also is helping for optimizing the network resources utilization by scheduling different IoT traffic based on their specific requirement. So with this, thank you for listening.
Okay, any questions for Constant?
You had a chart showing 4 different types of algorithms, like, decision tree, random forest,
Yeah.
Nearest neighbor. What's the GLM?
General linear model.
Oh, linear model. So what criteria did you use to determine which one is best? How did you score it?
Okay. Yes. When we run this test, we were using scikit library, and the scikit library has a score function. So we're just calling this score function to have this result. We didn't implement the machine learning algorithm. We're using an existing library.
Any more questions for Constant? Okay, that's a wrap. Okay, thank you. Please show your appreciation.
Thank you.